Okay, so in this video, I want to quickly remind you of the mean value theorem, and the timing might seem strange. Why am I introducing or reminding you of this theorem right now? It's because in our next video, we will prove the so-called fundamental theorem of calculus, which is the most important result of this course, of all of calculus, at least at this level, and we're going to need in the proof the mean value theorem. And the result, again, is very simple to state and very intuitive. So suppose you have the graph of a function, y equals f of x, that looks something like this. Suppose the curve, just for argument's sake, is increasing and concave down. Suppose this is the point x equals a and the point x equals b. So we assume that we have a curve that's differentiable on between AB and continuous on AB. Those are the only two assumptions of the mean value theorem. So the graph is y equals f of x. Then we consider the idea of connecting points AF of A and point BF of B to form a line segment. And you can ask naturally, what is the slope of this line segment? Well, draw down the perpendicular and the parallel to the x-axis and form a right triangle. Right? The slope of this line is going to be the change in y over the change in x. Change in x delta x, very obviously b minus a, the total length of our interval. Change in y, delta y, well, a change in y means taking the larger y value, f of b in our case, and subtracting the smaller y value, f of a. So that is the change in y. So of course the slope of this line connecting the point AF of A with BF of B is the change in y over the change in x, which here, as we have just found, is f of b minus f of a over the change in x, b minus a. So far we haven't done anything, right? We've connected 2 points, formed a line, found the slope of this line, and we've completely ignored the rest of the curve. But what does the mean value theorem say? What the result says is there must be at least one point between a and b where at this point the derivative of the function is equal to the slope of this line. And you can think of this as the average slope of the function. You see the total change in y of the function over the total change in x of our interval. So you can think of this as the average slope of our function on the interval from a to b. The mean value theorem says that the average slope must equate the instantaneous slope, therefore the derivative, at least one point between a and b. If you look at the picture, it looks like the tangent line here is essentially parallel to our line here. So if we draw down the line segment to the x-axis, you have the point, say, C. And again, draw its tangent line. The slope of this line is, of course, by definition, the derivative of the function at C. Right? By definition, the derivative of the function at a point is the slope of the tangent line. And because both lines are parallel, they must have the same slope, so the average slope of the function, the slope of this line, is the slope of the tangent line at this well-chosen point. Both slopes are equal. And that is the mean value theorem. That on an interval from a to b, if the function f of x is continuous and differentiable inside of ab, the average slope of the function on this interval must be equal to the instantaneous slope at a given point between a and b. Now for our application in our next video, proving the fundamental theorem of calculus, we'll need a slightly different form. So we'll just multiply both sides by b minus a, and that's the form that we'll be using. So think of it this way. F of b minus f of a is equal to, so total change in y, delta y, is equal to the derivative of the function at some point. C is some point between a and b, between these 2 points, times the change in x, right? Multiply b minus a to the right, and this will be the form of the mean value theorem that we'll be using in proving the fundamental theorem of calculus. So simply remember this. If you do f of b minus f of a, whatever b and a are, as long as f is differentiable and continuous, the difference between f of b and f of a is just the derivative at some point between these 2 points a and b times the change in x, b minus a. And with this, we'll have a very nice proof of the fundamental theorem of calculus, which, as you will see, will be connecting the indefinite integral, the idea of finding an antiderivative, to the definite integral, finding the net area below a curve.